Hi. Hello. Oh, sorry. Sorry, I had not turned my microphone on. Yeah, my screen is visible, right?
Yes, visible.
Oh, okay, great. Sorry for the delay. Okay, so good evening, everyone. Welcome to the week 3 problem solving session. Okay, this time's topics are week 3 problem solving session. Okay, this time's topics are week 3 topics. Okay, randomized algorithms, basically randomization, and polynomial identity testing, randomized quicksort, okay, and concentration inequalities. Okay, great. So I will also be uh, discussing the solutions to the previous week's assignment because it's released. It's well past due date. Okay, I'll also be discussing this, and well, sadly, I told you there was some kind of uh, inconsistencies with the weeks and the assignments. That's the each assignment had the content of the next week. So, as I said before, I talked to the instructor and it's fixed now. So, week 3 onwards, the assignments are correctly whatever week the content belongs to. But sadly, I think you guys had to catch up doing extra lectures because week 2 assignment was based on randomization, whereas randomization was this week's content. So yeah, that is one thing, but it's addressed now. So but I'll be discussed. So the good thing is today I'm discussing randomization, so I can even handle both the questions, including the assignment question. Okay, great. So let's talk about randomization quickly. So randomization is, so what is randomization? Well, if you have an algorithm, okay, that always behaves the same way. Okay, algorithm that always, okay, behaves same in every run. Okay, that is what is called a deterministic algorithm. Okay, the opposite is what is called if not. Okay, and it depends on what is stochasticness. That is what it's called. Then your algorithm is randomized. Now, what do I mean by stochastic? There is some probabilities associated. Okay. Now, what do you mean by probabilities associated? Well, if I need to make a decision, so this is what a deterministic algorithm looks like. It starts running. Okay, and say this is like the tree of decisions that it makes the same chain of if and else's every time, and then it ends, or maybe there are loops in between, and so on, and it ends. But a randomized, the working of a randomized algorithm is it comes across a point where it does not know what to do. So what it does is it actually tosses a coin or rolls a die. Okay, and since we always talk in terms of binary, usually in computer science, so we it's easier to think of coin tosses. So it tosses a coin, heads or tails, or that is 0 or 1, whatever comes in hand. It then branches from there, and maybe it tosses more coins on the way, and then it branches on the way. And this is how a randomized algorithm works. Now, what is an example? Well, quicksort, I think you saw in the lectures is an example. What is quicksort? quicksort is you have your array which you want to sort. Okay, 7, 3, 8, 9, 10, 1, 3, 2. Okay, you want to sort, and the mechanism is just that you pick what is called a pivot. Let's say I always pick the first element as pivot, that is 7. So on the left of 7, I'll put, and this is what is called the partitioning process. On the left of 7, I put everything that are less than 7. And on the right of 7, I put everything that is greater than or equal to 7. Okay. And for example, 3, 1, 3, 2 is less than 7. Okay. This is my pivot. And on the right of 7, everything that is greater, 8, 9, 10. Okay. And this is the first phase. This is the partition phase. Now what do? I recursively use quicksort the left half and quicksort the right half. Okay, I again apply quicksort algorithm. Maybe next time I choose 3 as pivot, and then I partition again. What is less than 3? What is greater than 3? And so on. The problem is, yeah. Okay. So first of all, what is the advantage of doing randomization, right? So this is a deterministic quicksort. Okay, I always choose the first element as pivot, but if I randomly choose the pivot always, the position of the pivot, maybe the first time I pick the third element, the second time I pick the second element, and so on. It so happens that quicksort performs much better. Okay. The deterministic quicksort, on average, okay, in fact, in the worst case, okay, it performs n square number of comparisons. So overall the running time is n square. Okay, worst case running time. And the randomized quicksort, the running time on average is n log. So you get a much better running time. Okay, using randomization. What do I mean by randomization? The pivots, okay, are picked randomly in quicksort. So why use randomization? Okay, we get a more efficient algorithm. Okay, we get a more efficient algorithm in terms of time. Sometimes even space, or other, it could be possible that other things are there, but overall we get a more efficient algorithm. And why do we get a more efficient algorithm? Why do we get a more efficient algorithm? Well, philosophically, it is that these worst cases are kind of rare in in most problems. These worst cases are rare. Okay. For example, what is the worst case when for quicksort? It is when the largest element is always picked. When the largest element is always picked, or maybe when the minimum element is already picked. That is when the array is already sorted. So that is the worst case. So that is pretty rare, right? So what randomization does is it avoids these worst cases by actually dabbling around the average cases more. So if the average case of the problem is more abundant than the worst case, then randomization actually helps you avoid those corner cases of worst case analysis. Okay. So yeah, go ahead.
So I have a query here, that is this possible that one particular run of the algorithm takes the exponential amount of the time, and still the expected running time, or an average running time of the randomized algorithm comes out to be of the order of n log n?
Can you repeat? Sorry.
So is it possible that a particular run of the algorithm takes exponential amount of the time, say time of 2 raised to the power n, but then the average running time of an algorithm comes out to be of the order of, say, n log n?
Yeah, it's possible, and that is the thing that I'm going to address. Okay.
Okay.
I'm going to address that now. Yeah.
Okay. And then one more thing that you wrote here big O for the deterministic one, and for the second one you wrote big theta. Is this by chance or intentional?
Yeah, this is intentional because it does not make sense much on talking about worst case in randomized algorithms.
I see.
You need to
But
do an
then,
average case analysis.
in the first case also, the order of n square is still the worst case of the quicksort only. So why don't we write it as a theta order of n square instead of the big O of n square?
Yeah, okay. Because theta of quicksort is, I think, n log n. That is one thing. See, I can write order n log n as long as I don't mean the worst case. Okay. Order n log n means that it is upper bounded by n log n, which is still fine. I don't, yeah. So it is what I mean by this is on average randomized quicksort takes order n log time. But I'm going to explain why I'm using this. Okay. I'm going to come to it. Okay. But yeah, so both these questions that you talked about are connected. Okay, so I'm going to address that now. Okay, so now we come to okay. So question is, why don't we use randomized algorithms all the time if they seem to be more efficient than deterministic algorithms? Okay. Well, ideally we want deterministic algorithms because we don't have what are called purely random bits known, a source of pure random bits known until now. Okay. By the way, okay, I wanted to ask, what is meant by randomness? What is meant by, say, random bits?
So random bits would be the outcome of a totally uncertain phenomena, like say the temperature of the room into, and really not. I mean, something uncertain will result into
Okay.
randomness.
Right, right. Okay. Something uncertain, something that cannot be predicted. Okay, cannot be predicted. Okay, so that is what is meant by randomness. And what is meant by independent? Independent means one trial does not affect the outcome of another trial. Okay, for example, I toss a coin heads, and then I toss another coin, I come to tails, and then I toss another coin which comes to heads, and then I toss another coin which comes to tail and head. Even though I tossed so many coins, and let's say it is always possible that at a certain toss, okay, at a certain I have a fair coin, okay, it's not biased. I keep tossing, and then all I get is heads, 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 heads. Can you tell what the next toss will be the outcome? The outcome, you cannot be able to tell if it's a fair coin. You may be into one of those you may be very lucky or unlucky, whatever, but you may be highly lucky to get this, but it is still not it is not still right to say that the next coin will definitely be a heads, or next coin has a higher probability of being a heads, and you are extremely lucky. What is the probability of this happening? Well, 1 over every time it's 2, and half times half times half times half, and so on, so which will be 1 over 2 to the 6, which is, you are so lucky that you got it in 64, 1 out of 64, so you're extremely lucky. And so you cannot tell, it could be tails or heads. Okay, you cannot tell. Another So this is what is meant by independence. And finally, I want to talk about what is called uniform. What is meant by uniform? Any idea? So what does it mean when I say uh, pick a item from a set uniformly at random? Or if I say, yeah,
So all are having equal chances of getting selected.
exactly. Uniform means all elements, okay, have equal chances, equal probability. This is what is called a uniform distribution, right? Uniform distribution. So, for example, a uniform distribution of set 0, 1 means outcome of coming 0 has probability half and 1 has probability half. Similarly, for a die, it is equivalent to uniform tossing a die is similar to sampling uniformly, you can say at random also, from 1, 2, 3, 4, 5, 6. Because each of these probability is 6. 1 by 6. And so on. Okay. So, okay, you have these concepts. Now I'll get into these expectations and this and that later on. Okay. But okay, so this is about randomization. Okay. Now let's come back to random algorithms. Randomized algorithms. Okay. So you can categorize them. Oh, I feel like there is a delay in the screen that I'm showing, because the screen that I'm showing, can you see randomized algorithms written? Okay, now I think you can see.
Yeah.
Oh, you can, right, Jatin? Okay. So, okay. So when you talk about randomized algorithms, okay, there are ways in which you can talk about the efficiency and the kind of loss incurred and so on. So there is yeah, another question that might come to you is like, if randomized algorithms are so good, so efficient, why don't we use it all the time? Well, we do use it practically, but why don't we just settle with randomized algorithms? Because randomized algorithms may not always be correct. Okay, randomized algorithms may not always be correct. There could be a loss associated. Okay, so there could be two types based on that. Okay, so the first thing is randomized algorithm, which is always correct, and the other type is which are not always correct, but we wouldn't like it if it is correct only once in, say, a billion or 2 to the n trials, right? We want certain guarantee, a good guarantee. It's not always correct, but fairly good. So this is where the concept of, for the right one, when it is not always correct, this is where the concept of probability comes. Okay, so not always correct but fairly good. So these are algorithms that are having some probability associated with them, that says something like algorithm A, okay, gives correct answer with probability at least p. This is the kind of statements you make of these kind of algorithms. And these, okay, and the left one, okay, which is always correct. If it is always correct, then it does not matter that it is randomized, right? We can simply make it deterministic. We can just fix the coin tosses and it can always be made deterministic, right? So, but why are we talking about this even? Because these kind of algorithms, you can think of these kind of algorithms that may not always be efficient. So now what I'm saying is the left one is always correct, but not always efficient. Okay, and the right one is but always efficient. What do I mean by not always efficient? It means that it is always correct, but it does not always run in polynomial time. Okay, it makes several coin tosses on the way, but it could be that in some coin tosses, some sequence of coin tosses, okay, it makes several coin tosses on the way and makes these decisions, right? But it could be on some coin tosses, it takes a long time, and in some sequence of coin tosses, it takes a short time. It ends here and it ends here. That could be possible for this. But whereas for the left one, the right one, okay, which are always correct but fairly good probability, okay, not always correct, sorry, the right one, which is not always correct, it is always efficient. No matter what kind of coin tosses you do, it will always end in short time. That is polynomial time. Okay. Always runs in poly time. Okay. Does not always run in poly time, but if it does not always run in poly time, if it always runs in exponential time, then what's the use? So we say that it again has a, but like we said, not always correct, but fairly good. But we are saying does not always run in polynomial time, but fairly good. Now, what does but fairly good means? On average. On average, over the choice of random bits, it runs in polynomial time. Okay. So on average, you take all the possible. So this is the first set of coin tosses, all zeros. This is the second set of coin tosses, 0, 0, 1, 1, 0, and so on. And this is the third set of coin tosses, 1, 0, 1, 0, and so on. So how many are there? There are exponentially many coin tosses, right? So let's say there are m bits, random bits, and there are 2 to the m possible coin tosses. Right, and let's say this one takes time n, this one takes time n square, this one takes time 2 to the n, and so on, and this coin toss sequence takes time n. Okay, take the average of all of them, is always polynomial. This is what it means. So fairly it runs in good time. So both of these algorithms have names, okay, and the first one, which is always correct, is what is called Las Vegas algorithm, and not always correct but fairly good but always efficient. Okay, these are what are called Monte Carlo algorithms.
So how is that possible that one term is exponential and still the sum of the terms came out to be polynomial?
No, it's possible. For example, say something like n plus n plus n plus n plus 2 to the n plus n plus n. So let's say this is, and take their average divided by, say, because there are exponentially many coin tosses divided by 2 to the n. Right.
So it is amortized runtime, we can say.
Yeah, you can say that. It that way you take the amortization to be the number of coin tosses. That's right. It takes amortized time complexity of polynomial. That's, you can equivalently say that. Okay, Jatin. Yeah. So this guy. So these are all the running times across different 2 to the n coin tosses, many coin tosses, and this will be something like a few of them take very little time. It can't be all polynomial also. That too is bad actually. Some take order 1 time, and then these factors will cancel out, and maybe you get something like polynomial. It's always possible for you to get. In fact, an example of Las Vegas, a good example of Las Vegas is randomized quicksort. Okay. And can you give me an example of Monte Carlo, where there may be some error, but it's efficient? Yeah.
So I remember that 3 coloring problem and 3 coloring problem. Yes. So
3 coloring problem, randomized algorithm. Coloring problem.
that does not use randomized algorithm, but then the chances of making errors is pretty low. But then that does not use randomized algorithm, I guess.
Oh, that does not use randomized. But I am talking about randomized algorithms. There is one done in the lectures. This week's lecture. Oh, there is one done in the previous week's lecture also. Actually, it was something to do with min cuts.
Min cuts, yes.
So which randomized algorithm did we do for min cuts last week? It is okay. I'll do that later, but I'll give you another example. Okay, another good example of Monte Carlo is polynomial identity testing. Okay, polynomial identity testing, which is done in this week's content, which will be the next thing I discuss. But before that, okay, I want to say that Monte Carlo itself has 2 kinds of categorizations. Okay. Well, what kind of answers can you have in these what are called decision problems? You can have 2 kinds of answer, yes or no. Okay, these are what are called decision problems. For example, polynomial identity testing says that is one polynomial equal to the 0 polynomial? Is one polynomial always 0 polynomial? Yes or no. Min cut is given an algorithm, or actually that is also a search problem, but you can always frame it as given a graph, is this set of edges the minimum cut? Is this function the maximum flow? And so on, yes or no questions, right? So it can always be that my algorithm says yes correctly always, if the answer is actually yes. And if the answer is no, then it may not correctly say no. It is always possible for that to happen. And okay, and one example is PIT. I'll come to that, but it says if answer is yes, probability of saying of A of X, algorithm on input X says yes, does not make too much error, but it still makes some errors, half, say, okay. And if answer is no, actually, it will definitely always say no. It will always say no. Okay, you can equivalently state it in terms of error also. That is, if yes, probability of saying no is if the okay, sorry, this is at least half, not at most. So probability of saying no when the answer is actually yes is at most half. That's what you can say. And if it is no and the probability of saying yes is exactly equal to 0, which means it never makes an error. So this kind of algorithm, okay. So this kind of algorithm is what is called a one-sided error algorithm. There is only one error on one side. Okay, and the other one is if yes, probability that algorithm says yes is at least half, and if no, then probability of algorithm saying no is also at least half. Okay. Okay, great. So this is it getting updated? My screen shows that there is a slight lag. Okay, I think now it's okay. Great. So this is what is called a double-sided error, two-sided error. Okay. Okay, so those things are done. Las Vegas, Monte Carlo. I'll come to PIT now. Until then, I'll check if any of these previous questions are answered. Okay, this is PIT, 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 perfect matchings. Okay, 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 Markov inequality. Okay, great. Okay, so can you answer the first question? Just try to charge my laptop.
A and D are correct because quicksort is the Las Vegas type of the randomized algorithm. It will always give the right value, correct output. And the Kargar's algorithm to compute the min cut was having some error associated with it in
Right.
giving the value. I guess.
That's right. That's right. Oh, actually, okay. The answers are also exposed here. But yeah, the reasoning is correct. Quicksort, I already told you that it's an example of a Las Vegas randomized algorithm because it never makes sense. It will always sort the array correctly. Okay, but okay, it's not a Monte Carlo, and Kargar's algorithm. If you remember, I had told last week that it can make errors. It may not always give a minimum cut, but it has a probability guarantee that okay, with so and so probability, it always gives you the min cut. Okay, so Kargar's algorithm is actually a Monte Carlo. So A and D are correct. That's correct. Okay, so we'll do PIT. Okay, PIT and bipartite matching. Okay. A lot of content this week actually. So polynomial identity testing. Okay, I'll straight out say the okay, first I'll define what polynomial. Okay, I assume that all of you know what polynomials are. Okay, polynomials are those equations, okay, of the form which can be written may not always be represented this way, which can always be represented as over x1 to xn can always be represented as some coefficient, okay, I in 1 to m, and some coefficient ci times x1 times x2 times and so on till xn, and each of them have some own power a1, a2, and so on till an. So and take the sum over them. For example, x square plus 3x equals 0. Okay, this may not be equal to 0. So that would make it an equation, but this is an example of polynomial. This is what is called a univariate polynomial. It has only a single variable. Let me check my battery. 30%. Okay. Okay, this is what is called a univariate variable polynomial, and xy plus xz 2xz plus x cube y. This is an example of a multivariate polynomial. Okay. What does polynomial identity testing say? Well, the original question, okay, polynomial identity testing says the following. Polynomial identity testing says, given p polynomial p, okay, over the field f x1 xn, okay, check if p, that polynomial p, is identically 0. What does this mean? For all values a1 to an in the field, p of a1 to an is always 0. Or in other words, if you write the polynomial in the simplest form, all the coefficients will be 0. No matter what inputs you give to the polynomial, it will always evaluate to 0. Okay, so that is what is meant by PIT. Polynomial identity testing. Now, this is an important problem which has many applications. Okay, but is it possible to do it in polynomial time? Given a polynomial, can I check whether the polynomial is identically equal to 0 or not? That is not known until now, whether it has a polynomial time. Yeah. Well,
So what's the purpose of using this field thing here? And moreover, can you give one example of, because this PIT problem formulation is not that clear.
yeah, sure. So because you have a polynomial, the polynomial is defined over a certain field. Okay, so what we look at, the polynomials we see in the let's say in the high school is always over, say, reals, but polynomials can be defined over complex numbers also. Polynomials can be defined over rational numbers also, right? And polynomials can even be defined over what is called f2 or gf2, which is simply 0, 1. Polynomials can be defined over this also, but you may say, how do I do addition, multiplication, and so on? You do it over mod 2. So 0 plus 1 is 0 plus 1 mod 2, which is 1. 0 plus 0 is 0. 1 plus 1 is 2 mod 2 is 0. So it simply becomes parity, XOR. So similarly, you can define, so this is what is called a field. Okay, but I don't want to get into the details of what a field is. But a field is the simplest definition would be a field is a set of elements where the most natural algebra works. Okay, which is addition and multiplication. And but after that, I need to get into too much detail. But it's not abstract algebra is not much required to understand this. Yeah. Okay. Fine. Right. Well. Okay. But yeah, it's important that you know what the field is. Why? Because especially in PIT, it may be so that a polynomial is the zero polynomial in polynomial is a zero polynomial in one field, but it is not zero polynomial in another field. Okay, so that is always possible. Can I give you an example? X1 plus 1 times x1 over 0, 1. This is an example. So if this is a polynomial, right? Is this the zero polynomial? Well, over reals, let's say.
So if I make this value as 0, so the value of x1 would be either 0 or -1, and -1 is not there over the real. I think it's there over the real. Yeah.
Is
So
that
we
over
have a
the
0.
reals? So over
Yes.
reals, it is not. It's not a zero polynomial, right? Because if
Yes.
I say put 2 here, I put 2 here. 2 plus 3 is 2 plus 1 is 3. 3 times 2 is 6. So answer is 6. So it's not a zero polynomial. It should always evaluate to 0. But if I take it over 0, 1, field f2, what is called f2 that I just defined, right? Then when x1 is 0, then this becomes 0 times um, 0 plus 1, which is equal to 0. And when x1 is 1, it is 1 times 1 plus 1. Which is equal to 1 plus 1, I just told you, is 0 in f2. It's just a XOR operation, which is equal to 1 times 0. 1 times 0 is equal to 0. So this polynomial surprisingly becomes a zero polynomial if you take f2 as the field. So now I think you get it why the defining a field is important. Yeah, Jatin.
I didn't understand how it is 1 plus 1 is equal to 0. Am I missing anything? Something?
Yeah, no problem. So I said if take this polynomial x times x plus 1, okay, if this is a polynomial over the field real numbers, okay,
Yeah.
then this is not an identically zero polynomial. Why? Because if I put, for example, x equals 2, then it becomes 2 times 2 plus 1, which is equal to 6. Okay, so this is not an example, this is not a zero polynomial over real numbers. Okay, this much is clear, right? That
Yeah.
okay. Now I'm doing something interesting. Okay, now I'm talking about polynomials. Now you must be see why we are talking about fields at all. Okay, because it's most natural to talk about real numbers, right? But there are things bigger than real numbers. For example, complex numbers, right? Complex numbers contain both real numbers and uh, contains real numbers, right? So there are bigger things than real numbers. Similarly, so you can ask the same questions like, okay, does it work for complex numbers? I mean, within complex numbers also, is it a zero polynomial? And so you can ask these kind of questions. And instead of increasing the size of the field, instead of going to complex numbers, I want to decrease it. Let's say rational numbers. Okay, let's say rational numbers. For example, x equals over field rational numbers. Okay, is it a zero polynomial? No, it's not a zero polynomial. For example, if I take something like 2 by 3, which is a rational number, 2 by 3 times 2 by 3 plus 1 is also a rational number. I don't know, you can calculate it. 10 by 9. Okay, this is also rational. It's right. It's not going outside rational, and um, and so on. This is still fine, and but it's not 0. So this is not a 0 polynomial, not a 0 polynomial over rational numbers, and so on. You can keep decreasing. I want to say, what is the smallest field possible? Well, it so happens, okay, that the smallest field possible is the set called 0, 1, which is also called F2. But what did I say? A field is where the most natural arithmetic you can do. That is, you can do addition and multiplication, right? So multiplication is clear, I think, because multiplication is definitely defined. 0 times 0 is 0, 0 times 1 is 1, 1 times 0 is 1, and 1 times 1 is 1. This is clear. This is your normal multiplication. But the problem comes when 0 plus 1 is 1, that's fine. 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1. Now we have a problem. Because this is 2. This does not belong to my field, right? So what algebraists do is they say that in F2, addition is performed always mod 2. Okay, including multiplication actually. So it's actually mod 2 addition, which means I do 2 mod 2, which is equal to 0. Okay. So now I'm back in the field. Okay, so in the field of F2, right?
So you have defined this type of arithmetic by yourself only?
No, it's not what I defined. It's a generally accepted convention.
In F2 field?
Yeah, in F2 field. For example, I can, there are results in abstract algebra which are about finite fields, which say something like, let's say F5, which is 0, 1, 2, 3, 4. Okay. So what are the operations? Addition is mod 5 and multiplication is mod 5. So if I do something like 3 plus 4 in F2, in F5, then what I actually mean is mod 5, which is what? 2. Which is 7, 7 mod 5 is 2. So it's not something that I defined, it's something that is standard. Okay. And yeah, but so what do I mean by this is, look at the same polynomial now. X times x plus 1. Look at the same polynomial now. X times x plus 1. Now set x to be, now check. Okay, let's say x is 0. Then what do I get? 0 plus times 0 plus 1, which is equal to 0. Good. X equals 1. What happens when, in the case that x equals 1? Then 1 times 1 plus 1, which is 0, but 1 plus 1 equals 2 in our natural, if we are working over reals or integers or, sorry, not integers, reals or rational numbers, it's equal to 2. But in our F2, 1 plus 1 is always mod 2. So 1 plus 1 mod 2 is 0, which is 0 times 1, which is 0.
So this is something that comes with the field only?
Yeah, it's whether it's only depend. No. It's not like it only depends on field, but I'm saying why the field is important.
Okay.
So I hope that was clear. Okay, Kishore, yeah, you had a question?
Yeah. So what we are trying to evaluate is, so of course the polynomial remains same, but if the field changes, the result will be a different one. So that's where we are giving importance to both polynomial as well as the field.
That's right. That's why it's important. That's why I didn't simply say, oh, P is a polynomial and then if it's identical 0. The importance that I mentioned field, that's correct. Yeah. That's why mentioning field is actually important. Okay, great. Okay, let me check my battery now. 18%. Oh God. Okay. Yeah. So you all know what the degree of a polynomial is, right? the total degree is sum of, oh, by the way, this is called monomials. Okay, each of these things, monomial, this is also monomial. These are monomials. Okay, these are coefficients. Okay, we used to call them terms in high school, but they are accepted. The general accepted term is monomial. Okay, total degree is the sum of degrees of each variable, the maximum over the sum of degrees of each variable in each monomial, which is just that if you have x cube, x1 cube, x square, x2 square plus 3x2 x3 plus 5x 1 x2 x3, then what is the degree? 3 plus 2, which is 5. What is the degree? Which is 1 plus 1. Okay, 1 plus 1. Okay, sorry, which is 1 plus 1, which is 2. This is again all the powers are 1, so 1 plus 1 plus 1, which is 3. So what is the total degree of the polynomial? 5, because it is the maximum. Total degree equals 5. So this question is straightforward here, right? What is the total degree of the polynomial? Well, first you have x to the 7, x1 to the 7, x2 to the 5, and so on. Just add the power of each monomial. The first monomial, 7 plus 5 is 12. The second monomial, 10. The third monomial, 1 plus 1 plus 1 is 3. So the total degree is the degree of the first monomial, which is 12. So that is the answer. 12. Okay. And okay, this one I won't do because this is redundant for the discussion right now. It's there in the first lecture itself. Okay. Okay, now I come to the Schwarz-Zippel lemma. Okay. How do I? Oh yeah. Okay. Okay, Schwarz-Zippel lemma says the following. So I told you it's not known how to do polynomial identity testing in polynomial time, right? But you can do surprisingly well using randomization. Okay. How? Okay, so Schwarz-Zippel lemma. So first I'll define an algorithm, which I'll call it algo SZ. Okay. Input is a polynomial P defined over a field F, x1, that takes variables x1, x2, and so on till xn. Okay. And so what is the algorithm? Okay. And P is of total degree D. Okay. Now what you do is you choose a set S, okay, from the field, set of elements from the field, okay, and it could be a set of real numbers, it could be a set of natural numbers, not natural numbers, real numbers, rational numbers, complex numbers, f2, f5, f7, whatever. Choose your favorite field. No, not your favorite field, sorry, the field that the polynomial belongs to. So choose a set uniformly at random, each of these elements. Okay. Now, what do? Evaluate P okay, there is something. Just give me one moment. Verify the algorithm. Don't want to make a mistake. Oh, okay. You don't you don't choose the set. Sorry. Okay. Suppose S is any set, okay, of size 2D, okay, and now what you do is now you sample. Choose some A1, A2, and so on till AN uniformly at random from the set S and evaluate the polynomial P over A1, A2, and so on. Okay. If 0, then output yes, otherwise output no. So this is a very simple algorithm. It says that take any subset of the field. Okay, take any subset of the field. Let's say you're talking about rational numbers, then take any 1 by 2, 3 by 4, 5 by 8, and so on. Just take any of this thing, but it should be large enough. That is, it should be of the set size should be around 2 times the degree. Okay, and now what you do is you pick any n numbers from that set and evaluate your polynomial. What Schwartz-Zippel lemma says that you can do PIT with a surprisingly high probability. Okay, so here is Schwartz-Zippel lemma. It says that if f is a okay, I won't write all this, so I'll just say the probability. Okay, probability that oh, okay, sure. Oh, okay, just one more. I'll finish writing
Yes.
this. Okay. Yeah, Kishore.
Yes, just before the step, right? So when we are trying to choose the set, I mean random like what S subset of field of size 2D we said.
That part is not random.
No, that's fine. But my question is, see, why we are taking only 2D elements? Suppose is it something? See, let us suppose the degree of the polynomial is 5. That means the size should be 10 elements.
Yeah. At least actually, here it's written 2D. It should be at least 2D. You can take larger.
Okay. So
That is fine.
equal to or
Yeah, you
not,
can
but
take
not less
equal
than.
to, or you can take larger. That is right. We just want the probabilities to work. See, if S is it's just the issue is just with this. If S is like less than 2D, then the guarantee you have is less than half. So right, if S the size of S is less than 2D, then the guarantee of the algorithm is less than half, which is not a good thing.
Okay.
We always want to achieve at least half.
Okay. Yeah.
Okay.
Yeah.
Okay. Good question. Yeah. So yeah, Schwartz-Zippel lemma says that when you sample from this set uniformly at random, okay, the probability that the evaluation is equal to 0 is at most d by s for a non-zero polynomial. Okay. Now they've said only about non-zero polynomial. What if it's a zero polynomial? Can you think about it? what happens to this algorithm in the case that it's a zero polynomial? Okay, it says the probability that. What about the probability of the algorithm when it's a zero polynomial?
So maybe
Huh.
it varies from 0 to 1, the probabilities. So when it is in 0, right, it will be 0 or 1. But when it is for non-zero polynomial, the probability varies from 0 to 1. Maybe like 0 to 0.1, 0.2, 0.3, or till at the extreme point.
For which one? For which one? Non-zero polynomial.
Right.
Okay, for non-zero polynomial, it's fine. They say it's at most d by s, the degree divided by the size of set you choose.
Right. See, the fraction itself gives the fractional probability like from 0 to 1. Is it?
No. So what this means is, if it is, so what we want to do is PIT, right? If the polynomial is equal to 0 or not. So let's say the polynomial p is not equal to 0. What should the output be? The output should be no, right? The algorithm should say no, this is not a zero polynomial, right?
Okay.
Right.
So the third step, you mean the third step? Evaluation.
Yeah, the third step. The third step. So if p is not identically 0, and it so happens that the evaluation on a1 to an is equal to 0, then I'll be saying yes instead of no.
Right.
Yeah, sorry, I forgot to mention this. So if p is not equal to 0, and if let's say f1 a1 to an, we chose a bad a1 to an, so bad that it is equal to 0, and it then outputs a yes. Because of the algorithm will output a yes. Then algo might output yes instead of no. But it says that it does not always say, it is not that it's highly probability that it does that. In fact, it is bounded by d by s. So in other words, what it means is it is equivalent to saying the probability that the algo says yes for a non-zero polynomial, that is, it makes an error, is bounded by d by s. Okay, I think now it's clear, right? Algo might output yes, which is an error.
So in that case, we are deviating from the point number 3, right?
In that case, because of point number, battery is low. Okay, yeah. In that case, the point, because of point number 3, I will deviate exactly. Instead of saying what the correct answer should be no, but I'm actually going to say yes.
Right.
Right.
So is it something we are contradicting with the theorem?
No, we are not contradicting with our theorem. The theorem, okay, this lemma says that the lemma actually does better than contradicting. It actually gives us assurance that, oh, it's okay, because the probability that it happens is actually not large. The probability is actually at most d by s. The probability that it says yes for a non-zero polynomial is actually not large. It's d by s. If we choose the set s to be very large, then it makes very little very little error. Is that clear?
Okay.
Okay. Now I want to ask you, what happens when p equals 0 case? Why did they not mention in the p equals 0 case? Or rather, what happens to the algorithm in p equals 0 case? How much error does it make? One moment, I'll try to get a charger. Okay. Please think about it meanwhile.